Saxon Advanced Mathematics, lesson 92. Welcome to a breather. This lesson is about probability, permutations, and combinations. So it is a step away from trig identities and heavy calculation type problems. And it'll just have a few simple kind of wrap your head around this ideas, and the calculations are super straightforward. Let's review probability as we have seen it up till now. Usually we have been, always, we have been dealing what are called mutually exclusive events. Let's take the example of drawing marbles from an urn. In this example, we have 3 red, 4 black, and 6 white. And we can find that the probability of drawing either a red or a black equals 7 out of, 13, right? That's the probability of the red plus the probability of the black. This is 3 out of 13, this is 4 out of 13. Add them together, you get 7 out of 13, right? You can look at it that way. We can also use a symbol for this. It's called P union B, which means a combining of the two. Union is associated with the word or because it means put both groups together. They're separate, but just add them together, okay? So this is a term that we use, and we use it's like a U symbol. So that's kind of fun. Now, there's another symbol that we use. The probability of where red intersects with B. This one means intersects or intersection, which means both. And in this case, what we're asking is, what's the probability of a red marble also being a blue marble? Impossible, right? It's not going to happen because these are mutually exclusive events. A marble is either red or black or white. It can't be both, okay? That's the kind of event that we have talked about up till now. But today's a new day. Now we're going to talk about events that are not mutually exclusive. We've got a couple different scenarios, but John draws us a fun picture first that I want to copy. And he presents it in a different way. This is a Venn diagram. And it reflects how many people in all? We'll make the dots and then we'll count them. All right, make the right number of dots. I've got 2 on the outside, 5 in the first circle, 2 in the overlap, 2 in the second circle, and then 2 more chilling in the edges. All right, I'll tell you what that means in a second. I'll give you a chance to copy. I'm trying to be better about that, you guys. I know I go too fast. And my hand covers it up and you can't see. And none of this is easy, is it? P.S. My plan for returning to in-person learning is as soon as I get vaccinated, I'm good to go. And then I'll leave it up to you and your family as to when you feel comfortable meeting in person. But I'm going to get vaccinated as soon as I possibly can. And I will let you know as soon as that timeline reveals itself to me, and then we can see each other face to face. I hope it happens before the end of the year. It should, but that would be really fun, wouldn't it? Okay, so what we have here is a diagram that shows us the boys in a group. It's boys and girls mixed. And this is redheads. My mother was a redhead. My dog is a redhead. I am not. None of my daughters are. My grandfather was. Okay, enough about that. Being a boy and being a redhead, those are not mutually exclusive things because it's possible to be a boy that's a redhead, right? It's not possible to be a red marble that's actually black too. Well, I mean, kind of. You could have a swirly marble. I'm really good at finding the exceptions. But these, you can see it's really obvious, right? Boys and redheads are not opposites. It's possible to have overlap, and that's what we have is redheaded boys right here. So when we want to find the union, the number of things like this, we have to take the number of boys plus the number of redheads. And then here comes the interesting part. Then we have to subtract out the number of redheaded boys. Okay, and that gives us, well, let's see what it gives us. Okay, so let's do this. The number of boys is 7, plus the number of redheads is 4, but we have to subtract out the number of redheaded boys, that's 2. That gives us a number of, let's see, 7 plus 4 is 11, minus 2 is 9. The number of this 9 represents 1, 2, 3, 4, 5, 6, 7, 8, 9. This represents the number of boys that are also redheads. So this is boys that are, this is the number of boys that are also redheads. No, that's not right. The boys and the redheads. Boys or redheads, right? It's the union of these two sets, but we can't double count the ones that are in both circles. My words are not making sense, but I hope my numbers and symbols are. So this helps us understand. We take the number of boys, one circle, the number of redheads, the other circle. We add them, but then we have to subtract out the number that are in the overlap. We can globalize that into an expression that looks like this. The probability of one event or the other event equals the probability of the first event plus the probability of the second event minus the probability of both. Okay? That's the formula. The formula is more complicated than the actual idea. We're going to do a couple examples that will help us. But this is the formula. The union of A, the probability of the union of A and B is the probability of A, probability of B minus the probability of A intersected with B. What? Okay, let's do another example. They will help to, the examples make it more clear. Okay. Example 92.1. A card is drawn from a full deck. What is the probability that the card is both an ace and a black card? No, I'm saying it wrong. The probability that it's an ace or a black card. Okay, the probability of drawing an ace. There are 4 aces in a deck of 52, right? We won't reduce yet. We might want to later because there's 4 aces, one of each suit. Okay, what's the probability of a card being black? That's half the deck, right? Because 2 suits are red and 2 suits are black. So half of the deck is black. So that is 26 out of 52. Now we have to figure out what's the probability that a card is an ace and black. And we say that as A intersect B. We need to know this number. Well, there's 2 black aces, right? Ace of spades, ace of clubs. So that is 2 out of 52. So to follow our formula, I'm going to write it all down again. the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersected with B. Okay, and this is what we're trying to find. We're trying to find if it's ace or black, right? And union, we remember, stands for or, and intersection, we remember, stands for both. Okay, so this is our formula. Those are our basic probabilities that we're going to use. So let's plug in. The probability of A is 4 out of 52. Probability of B is 26 out of 52. And the probability of it being both an ace and black is 2 out of 52. So we combine all of those and see the denominators all match. So I'm glad I didn't reduce in the beginning because then I would have just made work for myself. 4 plus 26 is 30, minus 2 is 28 out of 52. And I can reduce that, I can divide both by 4, and so I would get 7 out of 13. That's our final answer. That is the probability of a card being either an ace or, that's our union word, black. Beautiful. That's our answer. I hope it makes a little more sense. Let's try the other one. 92.2. An urn contains 4 white balls and 3 black balls. Okay, at first you're like, but wait, these are mutually exclusive. You can't be white and black unless you're swirly. But here comes more. 2 of the white balls are also rough. And 1 of the black balls is rough. What is the probability of drawing a ball that is either rough or white? Okay, so we're trying to find the probability of rough or, which is the union word, rough or white. Okay, we need to find the probability of rough. And we need to find the probability of white. And then we need to subtract the probability of the balls that are white and rough. Okay? And if you wanted to see a picture, let's just draw a quick picture. I don't want to draw a picture. I'm going to confuse you. Okay, never mind. Okay, the probability of balls being rough. Well, let's see. There's a total of 7 balls, right? And I see that 3 of them are rough. 3 out of 7 are rough. What's the probability of being white? 4 out of 7, right, are white. Then we subtract the number of balls that are white and rough, and that's 2 out of 7. This is a plus, right? So we add them together, we subtract the ones that have both qualities, and that will give us the full group of ones that are either or. And so the probability that they are both rough or white. I'm not choosing my words carefully enough, and my numbers are fine, but my words I keep using the wrong words to be specific and precise. The probability of choosing a ball that is either rough or white is 7 minus 2, 5 out of 7. Okay, and we call that the probability of rough union white. Yay! I hope that makes sense to you. Okay, Beautiful. That's all we're going to do with those. That's probability of either. And the important thing to remember with those is that the events have to be non-mutually exclusive. We have to choose qualities that aren't necessarily opposites like we used to. Okay, part B. We're going to talk about permutations, and we're going to talk about the formula that we've used. Now, this is the formula. We didn't always use it because a lot of times it's easier just to draw a picture and figure it out each time rather than use the formula. But what we're going to do is show how you can take the scenario and develop the formula, okay? So this is for permutations. That's what the P stands for. All right, and remember it's n things taken r at a time. That's what we're trying to show in all of this. Okay, so what we're supposed to do is take the permutation of 7 things taken 3 at a time. So 7 equals n and 3 equals r. And we're supposed to do a development for the permutation formula. Okay, well 7 things taken 3 at a time. Normally we would draw a box like this, right? And we would say 7, 6, 5. So we would say the permutation of 7 things taken 3 at a time is 7 times 6 times 5. Oh, yeah, that's right. Sorry, I didn't think I was counting down properly. Now, we know that if we want to do this on a calculator, or anytime we'd want to get a factorial notation, we know that it works if you do this, right? Right? Because then you can divide both of those away. And then we can write this as 7 factorial over 4 factorial, right? Because we can combine all of that, right? And this makes it a lot easier to solve. But we also notice that 4 is the same as 7 minus 3, right? This number we can get from these two numbers. So 4 equals n minus r. So we can write this expression as p to the n minus r equals n factorial, right? That's 7 is our n, over n minus r factorial, which is exactly what we said we wanted to get. Excuse me. So the point John's trying to make to you is that it's easy to see it when we have the numbers, and sometimes the formulas feel like they came from the moon. They actually are super easily derived from actual numbers in a specific problem. We can see that it's true. My only complaint, or it's not really a complaint, but my only observation is it's so easy to work the problem without the formula just by doing this, that sometimes it seems silly to try to remember this big fussy looking formula just for the fun of it. Okay, now when we do a combination, that's like when you're choosing people to be on a committee. It doesn't matter what order they're in, they're all just going to be on the committee, right? What we do is we take we take the permutation and we divide it by the number taken, the R value, okay? So what we have to do in this example that we have, we would take So the combination of 7 things taken 3 at a time would be 7 over 4 factorial, just like we had here, but we also have to divide it by 3 factorial. It's by the number of taken factorial, okay? So this is the regular permutation, 7 factorial over 4 factorial, and then we have to also divide by the number of things taken, which is 3 factorial. So this then becomes n factorial over n minus r factorial times r factorial. This is the extra part that we add for the combination. I guess I'll just do the whole thing. Okay, so the formula for the combination is the same as the permutation with just this little added piece. This removes the restrictions of order. It's hard to put the words to explain to that, but in combination, order doesn't matter because the order that we choose people in for a committee or a team doesn't matter. They're not going to stay in any particular order. They're just going to be on the team. So order doesn't matter, so we have to add that little piece to our formula. These formulas, should you memorize them? I mean, it's helpful to memorize them, but if you understand the problem, you can always derive the formula. And as you know, oftentimes in mathematics, that's almost preferable so that you don't waste bandwidth in your brain memorizing things that you can derive as well. But the important part of this, and I agree with John, is that I want you to see that these formulas are not weird or witchcraft. They just follow from what we already know how to do in the problems. So maybe that will help you remember them or even derive them if you need them. Guess what? That's the end of lesson 92. Yay! We did it. Another week. You guys, 4 more lessons in spring break. I mean, there's a little midterm in there. Don't forget that. But 4 more lessons and then no more new material until spring has officially sprung. Okay, I will talk to you soon. Goodbye.